Yeah, okay. The simulation shows that the voltage yeah, goes through cycles of up and down. First for on first it goes the voltage goes for less than 1 volt during 12 microseconds. Then it goes up to 5 volts, and yeah, I don't know how to explain this.
Maybe it's easy if you, or it's more clear if you first do the calculations. And look at my example in the course document and run.
Yeah.
I think it's on the next page. You can see that this is just a graph. There it is.
There's.
You see, and there I selected the correct formula. It's in the red rectangle, the lower side of the page that you can see right now. So you use that formula and look carefully at RA and what's RB. So maybe you can change in your PSpice schematic R1 and R2 to RA and RB. You can copy this formula, and then you have to use the values that you've chosen for RA, RB, and for C. And C, you have to write in your text that C1 is C in the formula. And then you can check with the calculations what will be the outcome of that calculation. And then it says the frequency in X amount of hertz. And then you can look at the graph in PSpice. You use your probe cursor, and then you can compare the values. You understand?
Yes.
Okay, so now just do all the steps.
Yeah, I will just first change this. So I copied this thing again. No, this is the updated. And there it is. Okay, so now I just have to change the values of the formula and resolve it. So the formula is 0.40 between RA is equal to 1 kilo ohm and plus 2 RBs. RBs is also 1 kilo ohm and all that multiplied by C, that it's I have a question. On the letter C means the value of all the capacitors, right?
Let's just see one.
Just C1.
So you have to write that in your text, that the C in the formula equals C1 in the schematic.
Okay.
So make a special note, a special sentence to anywhere to write down that C1 in the schematic equals C in the formula. You're in control.
We have this. Let's just make this more stylish.
Just take your time. You're doing well.
So now we just change the values. So it's 1.44 divided by 1K divided by 1K plus 2 1K multiplied by 10. And just going to resolve this very slow.
The last number in, you say multiplied by 10 nano.
10, oh yeah, 10 nano.
Yeah. And seeing the fact that everything is below the line, you have 1.44 and then divided by, now you need to place an extra set of brackets before 1K and after 10 nanos, that you where the cursor is right. Otherwise it doesn't go well. So behind the N of 10 nanos, you have to, no, that was okay.
Yeah, I'm just changing the brackets.
And yeah, yes. Now you have 1K plus and then twice 1K, and that will be divided by 10 nanos, and the whole answer, you divide 1.44 by the total answer of the rest. Now it's okay. You see that?
Mm-hmm.
Okay. Yes. And maybe, yeah, that's why maybe you can use an extra bracket also on the right side of 4 for 1.44. Okay. That was from my colleague York.
Okay, let's see. Yes. One point four. Oh, okay. Now 3K is 3000 multiplied by 10 nano.
If you have 10 nano, you multiply it by 1,000, you get 10 micros, and then by 3, you get 30 micros. So you don't need a calculator for that. You understand? Nano is 10 to the power of minus 9, and micro is 10 to the power of minus 6. So 3,000 times 3K. A K is 1,000.
4,000.
So 3K, so 1K, that means if I would multiply 10 nanos with 1,000, I get 10 micros, yeah? From 10 to the power of minus 9 nanos to 10 to the power of minus 6 micros. And then I have 30 micros, and then times 3, because it says 3K and not 1K. So once again, if we multiply 10K with 1,000 or 1K, then I have not 10 nanos, but 10 micros. And then just multiply that by 3, because I have 3K, not 1K. And then I have 30 micros.
30.
Yeah. You understand?
Yes.
Okay. I hardly ever use my calculator. Do it all by heart. Not everything, but a lot. So then now you use your calculator.
Yes. 14.4.
3. So 3 times 5 equals 15. So something below 50, and then in a small value, because you divide 1.44 by 30 micros. Please speak up. Let us know what you're doing.
Yeah, just I'm just working with my calculator that I really don't know where the things are. Okay. don't know if I put this right. They got
So 48 kilohertz.
yes.
In the example, the variables are different, so you cannot look at the example.
Yeah, I'm just.
You can look at your output from PSpice.
Yeah, I put this.
Pepijn, do you follow the story so far? Just to ask someone else. Earth calling Pepijn.
Sure. Sorry.
Are you following Christian's steps so far?
Yeah.
Can you tell us what's the main influence on the frequency of the output signal, Pepijn?
Nope. Yeah, I cannot follow it.
You cannot follow it, Pepijn. Why not?
I'm not smart enough. But
What can you explain to us, Pepijn? What is Christian doing? What did he just do? What was the calculation about?
I don't know.
Sorry?
I don't know.
You don't know.
No,
Have you looked? Have you been reading the
And
example?
my computer, or well, the call keeps on shutting off. Has to reconnect every time, so I cannot really follow the lesson.
But now it works. Teams works with you right now.
Yeah, but it still keeps on reconnecting every time. So yeah, that kind of
Can you,
sucks.
Pepijn, can you show us what have you drawn so far in PSpice? So
No,
can you show us your analysis?
no, I don't think that's gonna work because well, everyone is on the Wi-Fi right now. And nothing is working on my computer. Only Google is working. So
PSpice has got nothing to do with your Wi-Fi, you know.
no, but still, yeah. Oh, I thought you were working with KiCad.
Excuse me? KiCad, that's another. No. We're working with PSpice, man. This is simulation software. Did you start writing your?
Download? Fucking hell! What the fuck is this shit?
Fine. Did you start writing your own analysis document?
Yeah.
Can you show that to us right now?
No, I can't because PSpice is not on my computer anymore.
Then fix it.
Yeah, well, I've tried that 5 times, and every time it doesn't work. Just the whole system doesn't work. I don't know, something with a computer or something.
Then share your screen with us. Let me see it. Maybe I can help you.
I have to re-download it though, so like, yeah. Wait up. Desktop. Yeah, okay.
Do I stop sharing my screen?
No, I can share it at the same time.
Oh.
Wait, what the fuck? Oh man, what the fuck is this shit?
You shouldn't curse so much. You shouldn't curse at all. I saw that also what you wrote in the chat before. Please don't curse.
What's what?
Vloeken, niet zo vloeken.
Oh, yeah,
Curse is vloeken.
Ja, nee, dat weet ik.
And also in the chat you wrote something blah 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 this shit. Don't do that. If you do that at a company, they might fire you on the spot. They kick you out. Don't do that. That's not good for you, man. Come on. I'm just helping you.
Will they fire you for cursing?
Yeah, they do. They do. They sometimes they do, yeah.
Wow.
Especially if you're an intern. You should be polite and professional.
Yeah, no, I am polite, but sometimes I'm just like really, really, really annoyed.
Yeah, well, you have to learn to suppress that and to work with that in another way and learn to become more professional. You shouldn't curse. Yeah.
Yeah, well, yeah.
I gave you Peace Pies from a memory stick, remember? You don't
Yeah,
need
but I don't have
to.
that because I deleted it because it didn't work. So
Do you still have the files?
no, I don't. I deleted everything because it
Never
didn't work.
delete something that I give you. Always save it and even
Yeah.
make a backup.
Okay.
I'll
Am I
send
still
you.
sharing
I'll
my
send
screen?
it. I'll send it to you right now via a retransfer.
Yeah, on Outlook or what?
A retransfer via email.
Yeah. Oh, yeah. Okay.
Give me a minute, please.
Yeah, sure. Mm,
Don't curse. Come on. I hear again. Fuck. Check. Okay. Retransfer is running. Yeah, I got a verification code. Yeah. Check. 13. Two. That's. Oh, and there it goes. Okay. Okay, Christian, please share your screen again and just continue, okay? I just
Okay.
sent Pepina just sent the PSpice files to you. Be sure to install and run it as an administrator, otherwise it doesn't work.
okay.
So it may take a minute or so, but I send you the Spice information via email. Okay?
Okay. Thank you, sir.
You're welcome.
Okay. I don't know how to look at the frequency in the simulation.
You do look at the example, please. Please open the example in the course document.
Mhm. Okay.
You understand the example?
I think so. There are two proof cursors, or do I have to
No, just one.
use
and
one?
Yeah,
and
you place them
then
twice.
compare.
Yeah, so you start them. The output signal starts low. You don't look at the beginning. If you look at t equals 0 seconds, because these are the that's the startup effect. You look further down the horizontal line where you can really see that the signal repeats itself, the waveform.
Yes.
So always go a bit further, a few waveforms more to the right, then you're really sure, say about 55 microseconds. Oh, no, that's less. What is that? 48, 47 microseconds. You look at the lower part, it starts low. That's the high, you're low. Yeah, and then to the right, more to the right, yeah, there. And then a little bit to the left, so you start your cursor value. Yeah, exactly there. Until then it goes up, and then when it goes down again. You see, that's one wave until there, a little bit to the left. Yeah, so that's what I did in the example also. You measure with your simulation probe cursor information exactly the horizontal value from left to right for one wave, and that's the information you can use to calculate. Understand?
I think so. Okay.
So if you divide, if you have they call it the time for one period. If the frequency equals 1 divided by the time of one period. So if you know how the period is the time it takes for one wave, yeah?
Yes.
One waveform, I should say. So if you measure that, you know the horizontal values, the x values in microseconds. So if you subtract, what's the version on the right? 68 something, 69. You can look at the probe cursor window. So you get 69 microseconds minus, and what's on the low side? Is it 40 something? 48?
48, yeah.
So if you subtract 48 microseconds from 69 microseconds, then you have about 21, roughly.
Yeah, 21.
So 1 divided by 21 microseconds, that's the frequency of this signal. That's exactly what I wrote in the course document, in the example. You follow all these steps. You understand it better now?
Yes, now I understand better.
So now you know the frequency of the signal that this circuit generates with the values of RA, RB, and C1, which you've just set in your circuit at PSpice, generates the signal that we see right now. And you see you just measured with your probe cursor window, one wave shape takes about it's approximately, it's an approximation, about 21 microseconds. If you want to know, you just divide 1 by 21 microseconds. So 1 divided by 21 microseconds equals the frequency of this signal in hertz. And once again, I wrote all these steps down in the course document, so you can read, everyone can read the information in the document. And that's how you can check from your simulation, does it work like that with these specific values for RA, RB, and C1. You understand that, Christian?
Yes.
This is how you do that for all electronics. If you have an Arduino and you have digital write high and digital write low, and you say it's X amount of time high and X amount of time low. If the time high is the same as the time low, you have what they call a symmetrical duty cycle. Duty means when there is duty, when the voltage is high. What can you say about the duty cycle, what you see right now? Is it symmetrical or asymmetrical?
Symmetrical.
Why?
Because it repeats the same form always.
But is the time that the signal is low, is that the same as the time that the signal is high?
No.
No, so it's not symmetrical, it's asymmetrical. You see that?
Yes.
Now, if you go back to the the conclusion for this moment, before speaking about the duty cycle, you understand now how you can measure the frequency in PSpice.
Yes.
So we calculated, we looked at
the difference of time.
Yes, so 69 microseconds minus the 48 equals 21 microseconds. Frequency equals 1 divided by the time of the period. So that's 1 divided by 21 microseconds. And that's, did you calculate the frequency? Did you write this down in your Word document? Please switch to the Word document so we can see that.
It's not already switched.
Sorry?
You see the Word document right now.
So you still have to place the information in your Word document. Please do that right now.
Yeah, let me install this. Yeah. So I have this thing.
There's information in your Arduino course, and then you understand it even better because you will see it's the same. It's the name duty cycle. So if you're programming an output signal in the Arduino C, then you write digital write high, digital write low. Delay, you can do that with a delay. That's one option. First one that you learn. And if the delay time for digital write high and then after digital write low, they are exactly the same, then the duty cycle is 50%. The signal is the same, say it's 10 microseconds high and also 10 microseconds low, then they say the duty cycle is 50%. So we can check later on in this circuit, how can we play around, how can we fool around with changing some values that we can change the duty cycle. That's extra information. First step is now to calculate, how can you calculate the frequency of the signal? Yeah, the simulation shows that the cycle, that one cycle, that one cycle, maybe you can write between brackets waveform, that cycle equals waveform. So just after the word cycle, I would write between brackets waveform. Kevin, do you hear us? Are you still online? Hello, Kevin.
Yes, I am.
Can you explain to us in your own words what's the definition of duty cycle?
A what?
What is meant, looking at the signal that you can see in Christian's screen right now, with the definition of duty cycle?
It's like pulses of electrician, I think.
Yeah, well, yeah, it has to do with pulses, yeah, but what's the definition of a duty cycle? If you look at the pulse-shaped signal or wave shape that's on Christian's screen right now. Capital F, yeah.
I don't know. I think it has to like the ratio on how big the gaps are between or what's the rate the electrician is pulsing in.
The voltage, yeah. So the ratio between high voltage is low. Kevin, can you say about what can you say about the symmetry of the signal that you can see right now in the Christian's window? Is it a symmetrical duty cycle or asymmetrical, and why? Please explain why.
An asymmetrical.
Why?
Because the lows are less value than the top ones.
Less value. We prefer to say shorter in time, because in value we normally mean the amplitude. You mean in time?
Yes.
Yeah, okay. Yeah, that's correct. That's correct. So you understand that. Okay, that's really cool. And when Christian is ready with writing about how he measured in the simulation results the frequency of the specific signal, he has to check it with the calculations. I mean, Christian, you use the calculations from the information of your simulation, but you also have the formula of the data sheet. Remember?
Yes. Which one? This one?
So yeah, this one. So it says, what's the unit of the answer? 84,000 what? Tomatoes, pineapples, sandwiches, chocolate bars. 84,000 it says in the lower part. You have to write a unit behind that. What is it? Volts, amperes, something else? What is it?
This one is hertz, right?
Yes, capital H, small letter Z. That's from Heinrich Hertz. That's a Z, not an S yet. Heinrich Hertz is a German inventor, engineer, and he did a lot of research according waveforms. What's the definition of a waveform, and what's the relation with the time a waveform takes, and the time it takes for one waveform to repeat itself. He did a lot of research about that, and that's why Heinrich Hertz, why his last name has been connected to the unit of frequency. So the repetition time of a waveform is what they call the frequency in hertz. Yeah. Nice work, Kevin. Great answers. Doing good.
Okay. I will just write the formula with them for the frequency.
Mm-hmm. You can also look in the chat, in the Teams chat. Someone has been placing some information about it.
Oh, George. So this is, oh yeah, the pulse width modulation. We have to use this for Arduino.
So you see, if you learn more different things, let me say this. A teacher of mine, Henk Liebrechts, years ago, I was 13, he told me the following. The more you learn, the more you see that many things are alike, or at least look alike. That means the more things you learn programming in Arduino, you learn electronics now in a separate course, you see that many things are the same. You see here, you can see now in Arduino, what's the definition of duty cycle. You see 0%, 25, 50, 75, etc. And DC is just 100%. If you have 100% duty cycle, which you can see in the image right now, yes. And then it says analog writes 255. Why does it say 255? You have any idea? Yeah. Let me ask you the following question: How many bits resolution is the microcontroller of the Arduino?
Yeah, I don't know that. But I know that 255. It's the maximum that value that an analog write can handle.
That's true. That's true, and it's an 8-bit microcontroller. A very famous and popular one is from ST Electronics, the STM32, and that's a 32-bit microcontroller. If I show you this right now, oh, I have to switch off my background. Give me a sec, please, just to show you this. None. There it is. Look, this is an STM32. You can see that. You can see it. I have it here in front of my camera. This one. You see STM32F401, and it's a Nucleo 64, and that's this development board. A colleague of mine and myself, we engineered and we developed this development board just to show you. And this development board works with a microcontroller. There it is. And this one, let me see if I can zoom in. Can you read it?
No.
It's the Atmel 328P microcontroller, this one. This is in the DIP28 package. DIP, that's dual in plane. That means it's a 28-pin microcontroller, 28-pin chip. And in the Arduino Nano, here, my God, I have a million things over here. If you look at this, just to show you, there's the Arduino Nano. You know that one? You have it.
That's the one we have.
That's the one that you have. And the mic, this is a TQFP chip, and it's also the Arduino 328P microcontroller, but in a different package than this one. Yeah. So this is a large development board with the microcontroller. That's the same one like in your Arduino Nano, and it's an 8-bit microcontroller. This one, if I take this one out of the package, I have many different microcontrollers here. There it is, out of the package. And this is a development board. And the microcontroller, this is the microcontroller. And you see it has many pins. Like this. You see?
Yes.
And that's the STM. ST is a company. You can see here the company logo there, like this, ST.
Yes.
And that's a 32-bit microcontroller. You can see it like if it's a highway. You have an 8-bit microcontroller. You have 8 highways in parallel, so there can be many cars driving at the same time, adjacent to one another. You understand?
Yes.
So, and if each car would be data, information, digital write high, digital write low, that you have to do something. It's like an instruction, yeah? So if I have 8 parallel roads, I can have many cars going from A to B. But this controller has not an 8-bit, but a 32-bit. So you can imagine, just to name an analogy right now, you don't have 8 lanes, but 32 lanes. So a lot more traffic, a lot more data information can be transported at the same time. So this microcontroller is much faster than the microcontroller on this development board or on your Arduino Nano. You understand?
Yes.
It's just general information. I'm just showing you this development board, and yeah, you know pulse width modulation maybe already. You know digital write high, digital write low. You know that from the definition. You just clicked on the web links. And I'm just showing you this board, that there are many different development boards that people around the world, students and engineers, use just to learn to work with microcontrollers, just like your Arduino Nano is. Okay? That was my brief intermezzo about microcontrollers according to extrapolate on something like what is duty cycle and what is symmetrical duty cycle, an asymmetrical duty cycle. And Kevin just spoke about it, and he made about 0 mistakes. So Kevin, that was really well done. He spoke about the differences about symmetrical duty cycle when the signal is high and the time the signal is low, etc. Okay? Christian, what do you think of a short intermezzo like this? What can you say about that?
Yeah, it's interesting, and it helps a little bit that we can look at other things that are not 100% from the topic that we are looking at, but are related.
And you also see that Jörg sent some links, some web links from Arduino. You looked at the image from the duty cycle, that one exactly, the definition of the duty cycle. So you can change your software so that in software you can change the duty cycle. And now with electronics, you go back to your schematic, please, in PSpice.
Yes, and this one.
So you can, the duty cycle now, we changed the frequency, but we can also change the duty cycle if we want to. For that, you have to look at your schematic. And I know from Jörg that coming this Friday during your Arduino course, you will also learn more about duty cycle and pulse width modulation, etc. So you will learn how to change that in software. If you look in the example in the course document, please, Christian.
Yeah.
You go up a little bit further. That's the information of the data sheet of the chip. Yeah, even one page before this one. There it is.
Ah.
And there you can see there's information about the frequency, but you can also find information about the duty cycle. You see what it says? Output driver duty cycle. I can just see it on your screen. The lower part, it says output driver duty cycle. You see that? So the formula that I selected just as an exercise is the one above that. Frequency equals, and it says the sign, the equal sign, is like, they call that a tilde. It's 2 small waves. You can see that? Can you point it out with your cursor? Frequency equals, it's on this page. We can see it. Don't scroll, please.
Which one?
Frequency equals 1.44 divided by RA plus, that one.
This one.
No, not that one. One above that.
Yeah, frequency.
Yeah, that one. And you see at the sign after the word frequency is like 2 small waves. That one.
Yeah,
what does it mean?
Similar to.
No. It's similar to if the 2 lines are straight. You can see the next formula, the 2 lines, output driver duty cycle, these lines are straight. You see that?
Yes.
Kevin, do you know what's the difference between that, Kevin?
Between what?
Well, if you look at what
the straight
Christian
and the sawtooth, you mean?
No. Christian is looking at 2 symbols. The symbol on the right side of the word frequency, it's the equal sign. But that's weird. That's like 2 little waves. But for the next formula that says output driver duty cycle equals, and then TL divided, etc.
Yeah.
There I see the equal sign is 2 straight lines. But for frequency, it says equals 1.44 divided by RA plus 2RB times C. That's the equal sign is different. What's the difference?
That is because the frequency, how do you say that in English? It's like ongeveer.
Say it in Dutch. Ongeveer. That's an approximation.
Yeah.
Ongeveer. Ongeveer in English is it's approximate.
So that's
It's
like a sign for approximate this.
So I hope everyone sees this, that if you have a sign like this and there are two small waves, and then it means it's approximately what it says. So not exactly. And if you scroll down, Christian, please. Yeah, further down where you can see that I did the even further, even further, even further, please. Yeah, here you can see in red, the frequency is 480 Hertz. And if you go a little bit down on this page, I think it's on this page, or the next one maybe, it's nearby. Yeah, here it is, 470. You see? So, looking, and of course, I'm using the probe cursor and I'm moving that around. So my readings from my outputs, and the period t equals now is 5.0634 milliseconds minus 2970, etc. Where I place my cursor there I change the values a little bit. So if I say I make a little mistake, I do not really place the cursor exactly on the vertical line, then I make a small mistake. So I have a little tolerance because I do not really very accurately read the information for my window, my laptop window. You understand?
Yes.
So that's one reason. There's another reason. Can you name another reason why there's a difference between the calculations, the calculated frequency, and the measured frequency on your, if you would build the schematic on your breadboard, what could have an effect on the frequency of the schematic that we're analyzing right now? That's almost correct. Just kidding. You said,
Yeah.
I said, yeah, that's almost correct.
Yeah, in real life, the hardware could change the frequency.
If you please look at the schematic. Thank you. You use resistors RA and RB, and how stable is the value of a resistor, and what does it depend? The value of that resistor, RA, RB, whatever.
Yeah, normally the resistors have a certain amount of tolerance.
That's true.
On the value.
And what does it depend on, that tolerance? There's one thing that changes almost constantly. Sometimes it's relatively stable, but during the day it's changing. What is that? Starts with a T. Starts with the letter T.
Time?
No.
Oh.
Shall I just say it?
Yes, I have no idea.
It's temperature. If the temperature changes, then the value of the resistor changes. Just a little bit, but it changes. And if the temperature changes, then that means that 1K resistor, maybe it's 1K at 21 degrees Celsius, but in the winter, it freezes at night. It could be a few degrees below zero now during these, it's now winter. And if it's 21 degrees Celsius, or say -5, or next week, I believe it could be -9 or -10, then the value changes of that resistor. So that's something else that can change. It has a tolerance, the temperature tolerance of a component. And there's something else. How about that chip? So if you look at the data sheet of any component, then you see it always depends on temperature. It could be like a simple passive component like a resistor. It could be like a chip, the NE555 timer chip, which we are using right now. And that goes for everything. Even humans are temperature dependent. If we are feeling really cold and you're shivering and you're shaking a little bit because it's so cold. The fact that you do that, you shake with your muscles, is because it's a low temperature. And we bloat a little bit if it says last summer it was more than 40 degrees Celsius. It's really warm, and your body starts to sweat, etc., because it tries to cool down. So even a human reacts on temperature, and a resistor also reacts on temperature. So temperature has an effect on the frequency of the signal that this chip will generate. You understand?
Yeah.
Do you know how we tested this in the lab? If we could be in the lab?
With a multimeter?
No. We use your oscilloscope. We don't use the multimeter. We use an oscilloscope. So pin number 3 of the chip is connected to the measure probe, the probe of the oscilloscope, and the oscilloscope shows the signal just like PSpice does. So if you go one icon to the right, please. Yeah, no, the right, the other right. Show the signal, please.
Oh, this one.
Yeah, that one. So if we would be at school, and unfortunately we're not, so we can only do this with the simulation software with PSpice. What would we do at school if you build you assembled your PCB? And I believe everyone's done that already. So you can fill in first 10, I believe, first 10 criteria of your self-assessment. We would be at school, we could do the measurements on the chip, and then you would see the signal, Christian and the other students, the signal that you see right now in Christian's PSpice window, the green signal, you would see this on your oscilloscope. Remember?
Mm-hmm.
I can't say remember because we haven't done it. And that would look the same, or maybe not. And the maybe not is there are component tolerances. Yeah? There are temperature tolerances, all tolerances. And for the simulator, the resistor is relatively perfect. The chip is relatively perfect. Please go back to your schematic. Christian, yeah?
Yeah.
And I clicked on the icon that's on the left side if you run schematics, so the blue-gray one, not the yellow button. It's around in the middle, approximately in the middle of your window.
Which one? Ah, this one.
Yeah, that one. And do you see the word temperature anywhere?
Yes, here.
If you click on it, you see 27. You see
So,
that?
Yeah.
And
So these are
27,
ideal.
the 27 is the default value in PSpice. What if you make it 50? And click OK and run the simulation again. No, you clicked across. Don't do that. Please go back. Always click the close button, but check, is the temperature at 50? So please go back to temperature. The screen is free. Oh, yeah. Oh, it is. Okay. Run the simulation again. And I remember the values you had 69 and 48.
Let me change this one.
Oh, yeah. If you set these values in your transient value, you don't have to change the value what you just did in the probe, but it's okay.
Yeah.
And do you still have 68 and 49?
Let me see.
Maybe the value, maybe the difference is too small. I think that because we had 27 to 50, that's a difference of 21 degrees. I think you can hardly measure any difference. Maybe the numbers behind the comma.
Yeah, maybe.
This one was 48. Then you should have written down 48 points something, whatever. But go back to temperature, please. And let's make it 127. Just add 1. Temperature. And make it 127, just 127. So that's really hot.
Let me change.
Yes, now you're thinking. Now you don't have to set that all the time in your probe window. Nah! Remember to click close.
Everything's okay. Right.
Okay. It's in our system that we click on the cross when we close a window.
Now
And that,
let's look at this. Oh, now it. I think
you had 48 and 69. 69 became more than 70. You see that?
yes.
So yeah, so it increased. It changed a little bit.
Just some micros.
Yeah, so
Like
there's a little bit of difference and this chip is relatively stable because you use feedback. Later on in the second year you analog electronics and you study operational amplifiers and you study the effects of feedback in the system, and the NE555 chip uses internally feedback, and because of that you make something relatively stable. But you see there is a difference, because if I look at the value just around 70 microseconds, it was 96.8 or something, and now it's how much? 70 point. You can also use on the keyboard the horizontal arrows. So you can, if you do not use your mouse, you can use the horizontal arrows on your keyboard, and then you can make really fine steps. I think it works even more. I think it works more accurate than using your mouse. So about 71.
71, yeah.
Yeah, so this how much is that? It was 21 seconds. One period took 21, one waveform takes 21 microseconds at 27 degrees, and now it's how much?
It's 22.
Mm-hmm. I would like to do a check in between if we go to a chat, if everyone would switch on his camera right now, so that just in between, Christian, that we can see is everyone still online. So please, everyone, if you hear me, please switch on your cameras. And I can go into full mode, so I should see everyone, large gallery preview. And then it switches, and now I should see everyone. I do not see everyone. Nice haircut, Gareth. Looking sharp and fast, man. Cool. I'm thinking of swimming.
Thank you.
Yeah, looking cool. Looking. Where did Edie go? Hello, hello. So 1, 2, 3, 4, 5, 7, 2, 4, 6, 8, 10. There are 14 people. Do I see it correctly? Yeah, 14. 8 and 6. 14 people are online. Where's the rest? Well, I send a picture to your mentor so he can see who's the people who are online. So he knows who are not online. Okay. A question to everyone, except Christian, because he's conducting the analysis so far really well, by the way. Let's do this non-verbally, because if we all start speaking, it's not really clear. If you like the analysis that Christian is doing, then please do a thumbs up with your hand in front of the camera. Okay, so many people. Gareth, no thumbs up? Yeah? Oh, okay. Oh, everyone, so everyone. Okay, so Christian, that's a compliment for you. And I think well deserved. I think you're doing it quite well. Yeah. Christian, what do you think yourself of working this way?
Yeah. It's It's different.
Could you explain different?
Yeah, normally just work by myself, not with so much guidance.
And a question for the rest of the people who are online right now. Is it so that during some courses, if you have 1 or 2 hours, you're just listening 1 or 2 hours? Is that so? Some people are nodding, yeah. Some people are, yeah, maybe, comme ci, comme ça. Comme ci, comme ça, I see. So, comme ci, comme. So sometimes that is, and sometimes it's not. Okay. And Christian, can you say if you are doing things yourself, like you've done so far today during these almost 2 hours? We have 2 minutes left according to schedule. It's 12:43. Just reflecting right now with all of you, you understand. Christian, do you experience that you learn relatively a lot when you do things yourself?
Yeah. In this way, I think things I will remember better what I am doing and looking at, and than if I just stare at the screen and listen to the teacher.
Yeah, you remember things in more detail, and you're constructing your own knowledge, I think, because you're doing analysis, you're learning details, you learn how to make connections between RA, RB, C1, etc., the calculations, etc. Yeah. Okay, it's 12:44. Does anyone have anything to say about this so far? Would anyone like to say something? Okay. Shall we all thank Christian in this way? Please switch on the microphones and say thank you, Christian.
Thank you, Christian.
Yeah, thanks, Christian.
Thank you.
Thank
Thank you,
you.
Christian.
Okay, Christian, thank you. Okay, also from me. And I hope everyone is writing his own analysis document, that the coming meetings that we still have left, just a few, and that you can do a self-assessment. You have quite some material, and I hope that everyone learns a lot. Okay? Well, have a nice afternoon, and I see you guys next time. Okay? Bye-bye.
Have a nice day.
Have a nice day, guys. Bye-bye.
Have a nice day.
Houdoe.
Houdoe.